voltage controlled oscillator. Voltage controlled oscillator is an oscillator circuit which produces output frequencies depending upon the externally applied input voltages, and the VCO maintains the linear relationship between frequency, output frequency and input voltage, and the applied external voltage is also called as control voltage, and this VCO is also called as voltage to frequency converter. Why? Because with the applied voltage we are generating the frequencies, output to frequencies. That's why we are calling it as voltage to frequency converter. Generally using two versions of VCOs. One is NE by IC566 VCO and the other one is LM566 VCO. These are designed or manufactured by Cytex. Here this pin diagram is representing NE by IC566 VCO, and which is an 8-pin IC, and the VCO is consists of a special feature which is nothing but it produces two output voltages simultaneously. One is square wave output and the other one is triangular wave output, and these outputs are collected across the pins 3 and 4. Okay, now the capacitor is charging or discharging by a constant current source, and this constant current source is generated from this circuit, the constant current source, and we are applying the control voltage. Here I am applying the modulating voltage VC at the control voltage pin, which is nothing but the 5th pin. Okay, with this modulating input voltage the current is varying. According to that the capacitor charging and the discharging is varies. Not only with the help of modulating input signal, the output current is also varying because of resistance also. Okay, now the NE566 VCO block diagram is like this. It consists of 3 op amps. One is op amp A1 and the other one is op amp A2 and the third one is op amp A3. Op amp A1 is used as a buffer. I think you are all very well known about the buffer, which produces the output voltage equal to input voltage, which is also called as voltage follower, and op amp A2 is representing as a Smith trigger, and op amp A3 is used as a inverter. Here the capacitor charging as well as the discharging is controlled by using the constant current source. Now listen carefully to understand the operation of this VCO. First we are going to design the output of the Smith trigger is from plus V to plus 0.5 volts. Generally we are adjusting the Smith trigger output voltages are plus Vsat and minus Vsat, and in this case I am designing the output voltage of Smith trigger is plus V and plus 0.5 V. Now whenever RA is equal to RB, then the non-inverting input of the Smith trigger will be varying. How it is varying is if its output of the Smith trigger is plus V. If output is plus V, plus V into RA divided by RA plus RB. Here I am treating RA is equal to RB, so I am treating it as 2 RA. So we may get 0.5 volts. So that means whenever the output of the Smith trigger is plus V, then we applied the input at the non-inverting terminal of the Smith trigger is 0.5 volts. Similarly, if the output voltage of the Smith trigger is 0.5, then 0.5 into RA divided by 2 into RA. RA cancel. So 5 divided by 20, 5 1, 5 4 by 1, that is nothing but 0.25 volts. That means when the output voltage of the Smith trigger is 0.5 volts, then we are applying the voltage at the non-inverting terminal of the Smith trigger is 0.25 volts. So now listen carefully. The capacitor charging is always done by using these two levels. Whether it may be charging or discharging, that is done by using these two levels, 0.5 as well as 0.25 volts. Now depending upon the inputs comparison, we may get the output as plus V, or we may get the output as plus 0.5 volts. Suppose if my output of the Smith trigger is plus V, then what about my non-inverting input terminal of the Smith trigger? 0.5 volts. Then the capacitor is charging towards 0.5 volts. And if the charging of the capacitor is beyond 0.5 volts, then what happened? If the charging of the capacitor is 0.5 volts, this voltage will be applied to the buffer, then the same output will be generated here. Suppose if I am treating this voltage is 0.6, then the output of A1 is also equal to 0.6. That will be applied at the inverting terminal of Smith trigger. Now 0.6 is greater when compared with 0.5, then what you will get? You will get 0.5 volts. Why? Because minus Vsat will be generated here. My plus Vsat will be taken as plus V, and minus Vsat will be considered as 0.5 volts. If the inverting input voltage is high, then obviously I will get the output voltage as 0.5 volts. Once my output is 0.5 volts, then what happened to this input voltage of the non-inverting input of the Smith trigger, which is nothing but 0.25 volts. Now the capacitor will be discharged to 0.25 volts, and if it is below this 0.25 volts, then we will get the output as plus V. Again the capacitor will be charged to plus 0.5 volts. So the capacitor charging and discharging is always square wave. Why? Triangular wave. Why I am representing it as a triangular wave is the charging of the capacitor as well as the discharging of the capacitor is done by using same constant current source. That's why the time required to charge the capacitor as well as discharge the capacitor will be same. So here it produces the output at the buffer, that is the charging and the discharging will be nothing but the output of buffers. So output of the buffer is nothing but the triangular wave, and output of the Smith trigger. You already know that whatever may be the input you apply to the Smith trigger, always you are going to generate the output as a square wave. Here you are going to get the square wave output, and with the help of inverter, just we are inverting the square wave. That means if you are getting the positive pulse, there we are getting the negative pulse at the output of the inverter, and at output of the Smith trigger is the negative pulse. At the output of the inverter we will get the positive pulse. This is about the block diagram of VCO. Finally, the frequency of oscillations is F naught. F naught will be equal to 2 into plus V minus Vc divided by R1 into C1 into plus V. Here R1 and C1 are the external resistances and capacitance to this VCO, and Vc is nothing but the control voltage which we are applying at the fifth pin. That is about the frequency, output frequency of oscillations produced by this VCO with the applied external voltage. Now we are going to see the waveforms for this voltage controlled oscillator. The output of the buffer is nothing but the triangular wave. Already I explained how we are generating the triangular wave at the output of buffer. So first here I am representing the triangular wave 0.25. Like this we generated the triangular wave. Now what happened? Now listen. the output of the Smith trigger. Here I am going to represent the output of the Smith trigger. Already I told you that the output of the Smith trigger is designed to plus V to 0.5 volts. Yes or no? Plus V to 0.5 volts. Now tell me what happened if it is beyond that 0.5 volts. Immediately the output of the Smith trigger will be 0.5 volts. Already I told you, if this voltage is greater than this voltage, if it is 0.5 and if it crosses this 0.5, then immediately the output will be low. So here once it reaches 0.5, then immediately the output is low, and once it is below that value, then the output is high. That is, if this voltage is less than this voltage, then what happened? The output will be high. That's why here I am representing the square wave output as high, and this is the time required for the charging and the discharging, and one is the triangular wave output, which will be generated at pin number 4, and at the final one, which is nothing but the output of the inverter. Just we are inverting the output of Smith trigger, we will get the output voltage. So this is about the output of the inverter. That is the main output that we are going to get at the pin number 3. Here not the square wave output. Here, so not the Smith trigger output. Here it is output of the final one, which is nothing but the output of the inverter, and triangular wave, which is nothing but the output of the buffer. Okay, this is about voltage controlled oscillator. Finally, what I want to tell you is, always the output frequency of oscillations is controlled by using the externally applied input voltage. That externally applied input voltage is also called as control voltage. Because of the variation of the control voltage as well as the variations of the resistor, the current will be varied, and because of the variation of the current, the charging and the discharging of the capacitor will be changed. Frequency conversion factor. Voltage to frequency conversion factor is an important factor of IC566 VCO, which is represented as kV. Okay, what is kV? kV is nothing but delta F0 divided by delta Vc. That is the ratio of change in the output frequency with respect to the change in the applied external input voltage is called as voltage to frequency conversion factor, which is represented as kV. We all frequency of VCO is equal to 2 into plus V minus Vc divided by R1 C1 into plus V, where plus V is the supply voltage, and see this one, for the voltage to conversion factor kV, delta F0 is nothing but the change in the output frequency with respect to change in the input supply voltage. So delta F0 will be taken as F0 dash minus F0, where F0 dash is the new frequency and F0 is the original frequency, and delta Vc will be taken as Vc minus delta Vc, which is nothing but the change in the input voltage. Now first I am going to write F0 dash. What is F0 dash? F0 dash is equal to 2 into plus V minus Vc minus delta Vc divided by R1 into C1 and V plus V. And now I want to calculate F0 dash minus F0, which is nothing but delta F0. That will be taken as 2 into plus V minus 2 into Vc plus 2 into delta Vc and minus 2 into plus V and then plus 2 into VC divided by R1 C1 and into V. Here this one and this one will be cancelled, this and this will be cancelled. Finally we will get delta F naught will be equal to 2 into delta Vc divided by R1 C1 into plus V. From this we can write delta Vc. Delta Vc is equal to delta F naught into R1 C1 plus V divided by 2. Okay, so this is about the change in the supply change in the applied input voltage, which is nothing but the change in the output frequency, which is delta F naught, and input voltage is delta Vc. From this we have to calculate kV. kV is what? kV is nothing but delta F naught divided by delta Vc. From this we calculate the value of kV. Modulating input voltage and the control voltage will be taken as 7 by 8 plus V. Now the original frequency F naught is equal to 2 into plus V minus Vc divided by R1 into C1 into V. So which is represented as 2 into plus V minus 7 by 8 into plus V divided by R1 into C1 into plus V. Yes or no? Just substituting that values. From this what we will get is 2 into 8V plus 8V minus 7 plus 7V divided by 8 whole divided by R1 C1 into plus V. So 4, that is 1 by 4 into plus V, which is nothing but 0.25 plus V divided by R1 C1 into plus V. So plus V cancel. We will get it as 0.25 divided by R1 into C1. From this expression write down R1 into C1. What is R1 into? That will be equal to 0.25 divided by 2 into delta Vc divided by delta F naught into plus V. So now R1 C1 2 into delta Vc divided by delta F naught into plus V. So finally F naught will be delta F naught. So normal F naught will be 0.25 divided by 2 into delta Vc divided by delta F naught into plus V. So delta F naught divided by delta V will be taken as kV. Okay, finally from this kV will be represented as 8 into F naught divided by plus V. Frequency conversion factor kV. By using this value we can easily calculate the voltage to frequency conversion factor. IC566 VCO. First feature is wide supply voltage ranges, that is from 10 volts to 24 volts, and the second one is large linear range characteristics. The linearity range between the output frequency and the input applied voltage is very large, and large power supply rejection, very large value for the power supply rejection. And the fourth one is the frequency can be controlled by using current, voltage, resistor and capacitor. Last but not the least is high temperature stability. These are the main features of the IC566 VCO. Into the applications of VCO, one is FM modulation. So the VCO will be used to generate the frequency modulated signals, and not only FM modulation generation, it is also used in the digital communication. It will be used as a FSK demodulator. While you are going to construct the original message signal by using the FSK demodulator technique, in that case also you are going to be used the VCO, voltage controlled oscillator. And the next one is signal generator. Just now we have seen it that the VCO is used to generate the square wave and triangular wave. And the third one is which we are all very well known application is VCO is used as a function generator. Function generator generates different frequencies with the applied voltages. That's why VCO is also used as a function generator. And next one is it is used as the tone generations, single tone generation as well as the double tone generations. We are using this VCO. Not only these are the applications, we may also use it in the frequency multipliers also. And VCO is an important block in the phase lock loop. So all the applications of the phase lock loop is also coming under applications of VCO.